My name is Prashanth. I work at Kuzu, and as the title suggests, Kuzu is an embeddable, fast, and scalable graph database, and it's designed for analytical workloads. So I want to first start by making a quick introduction to what topic we're covering. I know a lot of people may be familiar with graphs, and sometimes they're called networks in the literature. But graphs are among the most natural data structures to represent enterprise data. And the main reason for that is they facilitate an object-oriented modeling approach. And if you're used to relational databases and relational data modeling, graphs go one level beyond that. They are even more object-oriented. Now, the meaning of object-oriented can take on many forms, but essentially you have nodes that are connected to other nodes, in this case an entity. Each node represents an entity in the real world, and those entities are connected by relationships, shown as edges in this diagram. And because of the way the real world is organized, these form very interesting structures. So in today's workshop, we'll actually be looking at one of these examples, and I'm hoping that the practical nature of what we're doing will illustrate this a lot more. So I'll start by highlighting the goals of the workshop. We'll go over the basics of the Cypher query language for graphs. We will gain an appreciation for queries that are hard to answer in SQL and relatively easy and intuitive in Cypher. And the main class of queries that we would be doing is recursive querying. We'll showcase flexible join sequences and how they are useful in identifying insights from your data. We'll look at pattern-based querying. And we'll also look at graph algorithms, which most people have studied in their Computer Science 101, but this is a more, I guess, hands-on approach to seeing how they apply to your data in the real world. And of course, nothing is complete without visualization, because graphs, when visualized well, are really, really fun to work with. Now, the model that we're going to use is called the property graph model. You may have heard this referred to as the labeled property graph model if you're coming from other systems. But I'll refer to it in general terms as a property graph model. The data here shows the relationships between people and cities, and people who follow each other and people who live in those cities. Now, the leftmost side of this figure shows how you would model this in a relational database. You have a relational model where you have a person table, a city table, and a follows table and a lives in table. And the relationships between these, they're called relations in the RDBMS systems. They are implicitly defined by a foreign key relationships. So the columns that are relevant in the follows and lives in table are defined as foreign keys on top of their parent tables, which is the entity tables here. And the primary key columns are the ID columns on the left. Now, that's one way of doing it. You could also just as well move this into a document database, and that is a different approach where you have these JSON blobs, semi-structured blobs of information. Each JSON blob represents the same data, but you're storing each data as a key value pair. And you're allowed to have nested JSON here. So follows in this case might be an array of IDs that each person is connected to, and that can grow arbitrarily large. Essentially, what we're trying to explain here is property graph model is an abstraction that does exactly this, except that it's more visual and more intuitive to the way you might think about the relationships. The person follows a person, and you might draw that using an arrow like this. Person lives in a city, that's also shown directionally. And what the property in property graph model means is the fact that you have key value pairs attached to these entities. So a person has an ID, a person has a name, same for city and the city ID. So I'll go into the characteristics of Cypher. The first and foremost thing that Cypher needs to achieve is it needs to be SQL-like, because the power of SQL comes from the fact that it is a declarative query language. You don't need to tell the computer, provide the exact imperative instructions. It's compiled down to logical operators and physical operators, and that's where the power comes in. You explain the intent of what you want to do, and the instructions compile down to machine code. So Cypher achieves the same thing, except that the clauses are slightly different, where you might be used to select, from, and where in SQL. In Cypher, they are replaced with match, where, and return clauses. And the syntax is very intuitive. You have nodes represented by these parentheses, the curved brackets, and the edges enclosed in square brackets, but importantly, you have an arrow, a direction of a relationship that is specified using this arrow syntax. And essentially, a match is performing the function of a from in a SQL clause. A select is performing the function, or rather, a return is performing the function of select. Where is, of course, a predicate where you're doing filtering. So the idea is the same. And in the end, most query languages like Cypher, they're compiling down to relational operators. I think that's the key thing to take away from this. And that's kind of where Cypher comes from. It's designed with a specialized syntax and functions for graphs. And this is exactly what I was referring to, which is a property graph model. Cypher is a query language for property graphs. So we'll go over the benefits of graph databases and their query languages. The first is the idea of recursive querying and the notion of paths. So assume you have a financial transaction network like this, and you're asking a question, give me the shortest path of money flow into Bob's account from other accounts. And Bob here is this node on the right. So the money could have come into Bob's account from many sources. What this query is doing in Cypher is saying, give me the path, match the path that matches an account that did a transfer. And most importantly, you have these two things here, the star and the shortest keyword. The star syntax is what defines a recursive query, in the sense that you didn't tell it how many joins it needs to do. It might have to do an arbitrary number of joins. In SQL, you needed to explicitly say join, join, join as many times as you needed to join. So this is the key idea that you're introducing when you bring in a graph model, is that you have specialized syntax, give me the shortest path using this little clause here, and the star, which is called a clean star operator. And that is essentially saying it's an unbounded recursive query. Now, I haven't shown it here, I will show it in the workshop, but recursive queries are objectively harder to formulate in SQL. And we will go over an example to illustrate that. The other interesting thing about Cypher is flexible join sequences. Say you modified that question just a bit. You say, give me all direct or indirect paths of money flowing into another person, Eve's account. This time I use this clause. I say match account, transfer star 1.3. What this dot syntax says is lower bound and upper bound of the length of that path. And this is an example of what we mean by flexible. You could have chosen to return either parts of length 1, parts of length 2, or parts of length 3. By length, I mean each of these edges is considered a hop, and you might hop 1 time, 2 times, or 3 times, and n number of times, depending on what you choose. So this, again, is not straightforward in SQL. You need to actually be very explicit about the number of hops you're doing, or use recursive querying in SQL, which, as I mentioned, is not as straightforward. The other very useful feature of Cypher and other graph query languages is the ability to query patterns. Now, a pattern is essentially knowing an aspect of what you're trying to query on up front, and the ability to express that in a very natural way. So in this case, the diagram is a bit fuzzy, but essentially you have financial institutions that transfer money to each other. What you can do is be very explicit about what patterns you want to match on. You could say in this red blob on top, you could say, give me all the outgoing transactions that are less than $100, whose subsequent outgoing transactions value is less than that initial value. Now, why is this useful? If let's say you're trying to track down something like fraud or financial crime, you would want to only filter or narrow down on transactions downstream that are lower than or equal to the number that came up from upstream. Because if the number is higher, that essentially means there is an additional source coming from somewhere else. So doing this via a directional query approach, as shown here, can actually be very, very intuitive and not only help you get insights faster, but also ease the mental model that you have while you're doing this task. And I think the most interesting thing about this is the way you apply algorithms for machine learning or in general analysis on your data, the idea of entity-oriented questions. An entity-oriented question is, you know that your entity is of interest. In this case, let's say we're interested in accounts. So what we can do is ask questions specifically about that kind of entity. So you could run an algorithm like PageRank, which is an centrality algorithm that shows which accounts are really important in the network. On the other hand, you might want to create node embeddings based on the neighboring nodes of the account nodes. Account is connected to person, location, and so on. So having a node embedding, there are many algorithms like GraphSage and Node2Vec and other algorithms. So assuming you compute the node embeddings, you're essentially encoding the structure of the graph in that embedding. This is very different from the LLM natural language embeddings that you may be used to, where you're doing an implicit sort of fuzzy connections between entities there, whereas here these are explicit connections. You know upfront that a node is connected to a particular kind of node, and that topology or that structure is actually encoded in those embeddings, and those have value downstream for machine learning tasks. So this is a very powerful feature of graph modeling. So I'll end this quick presentation by mentioning the key feature of Kuzu that is, I guess, something that you may not have come across in other graph systems if you worked with graph databases before, is that the label property graph model is not new. It's been around for 15 years. Neo4j introduced this, I think, in 2008. So the diagram that I showed before, which is this node to different nodes being connected with these property values, it is indeed a property graph model, but they refer to it as the labeled property graph model, where each node has a label. In Kuzu, on the other hand, the underlying model is the same. It's still a property graph model, but the underlying storage mechanism is not the same. We use the concept of tables. And it's interesting that the words are rhyming. That was unintentional. But you could think of a table in Kuzu as a label in another graph database. And this is very intuitive for people who come from SQL and relational databases. If you come from DuckDB, Postgres, you are very familiar with the idea of person nodes, tables that represent entities, and related tables that represent relationships. So Kuzu essentially is, you could say, like an abstraction on top of that model. Everything is a table, a node or a relationship table. But why is this done? The reason is, by adding tables, you're adding structure to the overall storage layer. And when you know the structure of your data beforehand, when you know the types of the data types, you know what kind of overall table structure that you've defined up front, you can apply techniques like columnar storage optimizations, vectorization. This is not possible in systems which don't apply this, like label property graph systems, where you have record-based storage. You process data one tuple at a time. So when you run a recursive query in those systems, you are still collecting tuples in intermediate steps of the query processing pipeline, one tuple at a time. Whereas in Kuzu, the vectorization can kick in, and there are many other methods on top of this, which I'm not covering here. But from a technical perspective, there are other performance-related optimizations that you can apply thanks to the columnar storage that it uses. So that's an important point to note as we go into the working examples. So it's time to start with the workshop. If I can ask everyone to connect to their Wi-Fi, and yeah, go ahead.
Question. Could you please a little bit discuss the embedding aspect of the Kuzu? I didn't really get what do you mean by embedding. How do you use this embedding function to find a similar pattern base, like a pattern base?
Right. So I wouldn't call it a pattern-based embedding. So if you read up on GraphSage, actually, that's a machine learning approach where you essentially apply a function on the graph structure that you have under the hood. The reason I've wrapped it in an F there, the function is essentially you're transforming the underlying structure of the graph into a vector representation that is attached to each node, right? But it's a training process. Just like any other embedding, you are training these embeddings. But unlike conventional text-based embeddings, you are training it on the graph. So you would use a framework like PyTorch Geometric to actually, it's a deep learning framework, so you would use that to compute these embeddings. And then each node is given a value, like a vector representation. That vector representation encodes the neighboring nodes based on the graph. And that is very useful information now, because essentially, depending on the structure, you see the yellow node there is connected to red nodes. So it actually reveals something about that graph. And this is useful for downstream pipelines where you actually can use this. In fact, Microsoft did this in their GraphRag paper. If you read what Microsoft has done, they're using node embeddings in their graph as a complement to the vector embeddings that they computed for the vector retrieval.
Awesome. I guess I got the whole idea. I've worked with the graph embedding a little bit.
Sure.
I'm wondering that, let's say you have two same structure, but with the different nodes and relationships. Probably this is your algorithm that you have
Right.
implemented in this package.
Yeah. So let me be very clear. This is an ongoing work. This particular syntax that you see here is not currently available in the release that we have right now. This is an upcoming release that we're going to be doing. The reason I mentioned it here is for this workshop, I will not be going into how to compute the embeddings, but I will showcase how Kuzu can be used as a backend to machine learning pipelines. Yeah, go ahead.
Thanks for the talk. I have one question because I work with the graph.
Yep.
And your network is very, very huge.
Yep.
And lots of nodes. How to save them? Because for me, I use PCA or the user spectrum.
Yep.
Is what you use as well?
I'll come to that in a bit. So this is obviously a downstream thing. I want to first, I guess, introduce the idea of working with the database, but the goal of this is to show that the database functions as a backend for machine learning, right? I will come to that towards the end of the workshop. So yeah, I think let's just get started with looking at the repo. I hope everyone's managed to, actually, yeah, you can just go to github.com/KuzuDB. Actually, I'll show how I normally do it. And instead of I'll go to the home page, which is the organization, and I will search for TMLS in the repos, and you will find this first example here, TMLS24 workshop. So go ahead and clone the repo, and I'm hoping everyone has Docker installed on their machine, or at least has a way to install Docker on their machine. Awesome. So I try to make the usability aspect very as simple as possible. I don't want to have Python dependency hell that everyone faces on a daily basis. So I have a very clean way of managing Python environments. I don't know if everyone else is happy with their way of doing it. So I will show how I do it for my workflow, but you are free to use pip or poetry or the million Python virtual environment managers that you have. If you don't want to use Python, that's fine too. You can do the initial part of this workshop by just installing Docker and following the instructions. So I'm going to explain my first step. The first thing I'm going to do after cloning is I have my repository here. I have these directories, data, DDL, Python, SQL, and so on. And I will quickly show what I have in this Docker compose file. Essentially, what we're trying to do is we're trying to launch this application called Kuzu Explorer. And I'm pointing to the dev image because I want the latest cutting edge features of our new release that's coming out next week. But yeah, and normally you would just use the latest tag here. Just for this workshop, I'm using the dev. Now, the key thing here is I'm opening the database in read-write mode. I will explain the difference between read-write and read-only when we come to that. I'm pretty sure the issue will come up, and I will explain why you need to know this. We are exposing port 8000, so we're going to be able to access the database on a local host on port 8000. And I'm mounting two volumes here. One is this database directory, example DB Kuzu, to the Docker volumes database directory, and then the local data directory, which is on my left here. I have 3 CSV files, account, person, and transfer. And it's mapping to the data directory as well. So that's essentially what the Docker Compose is doing. It's a very simple Docker Compose file. It will download the image for you. And once you launch it, you'll be able to access the browser, and we can start typing in our stuff there. But let me walk through the repo and explain what we're trying to do. So at a very high level, the workshop is divided into 2 parts. The first is use Kuzu and Cypher to get comfortable with the idea of working with graph data and data structures. Once you are familiar with that, then the machine learning aspect becomes a lot more intuitive. So that's part 2 of the workshop, which is we will first run a graph algorithm on the graph. Then we will look at how to use PyTorch Geometric Kuzu as a backend to PyTorch Geometric. So any downstream machine learning pipeline that you were doing in PyTorch Geometric should seamlessly work with a Kuzu backend. And that's very powerful because you had all this work you did upfront to organize your data, to verify that the data makes sense. You did a basic analysis on the data. Once all of that information is in your head, it should be a lot more intuitive to apply a machine learning pipeline to that backend. And then, of course, this is an LLM-dominated era that we live in, so I will have to, of course, go over a bit of LangChain, and I'll actually explain some interesting observations I've had as I've gone through the whole question-answering exercise using Cypher and graphs. Okay, so the first step is you can run this command, docker compose, first cd to the directory. So I'm going to do that here. I'm already in the local directory. I have all my files in here. I'm at the level of the docker compose. So I'm just going to do docker compose pull. So it will pull the latest image, and I will then do a docker compose up, which is running the container. So to make it easier to see, I will just, so if you look at the bottom of the screen, this information is very useful to know. We are accessing the database in read-write mode, so I can write data to the database now in this container. I am using this particular version of Kuzu. This is really important to understand. The storage version is 27. Number doesn't matter, but the idea is the storage version has to align between what Explorer expects and what your database is actually stored as. So when you create a database, I'll show the database directory once we create it. It'll become very clear. So we have port 8000, and I'm going to open localhost port 8000. So this is the UI that we are going to be looking at. And there are these tabs up top. I've got a shell editor, kind of like a terminal, where I enter my queries. I have a schema tab where I could, in theory, add nodes and relationships using, I don't want to be adding it manually. And then I could explore a dummy data set here using this simple example. And then I have a settings tab, which I'll go over. So in the shell window is where I type my Cypher code. So what I'll first do is I will go to the DDL directory, data definition language. For reference purposes, I will work in both Kuzu and DuckDB. And DuckDB, as you know, is an embedded relational database. So think of it like an analog to Postgres, but much easier to use and set up. And I have a SQL version of this, and I have a Cypher version of this. So I will first showcase what I've done here in Cypher. Actually, to make things easier, I'm going to close this and open this in a separate terminal window so I have an uncluttered UI. Docker compose up, and then refresh. Okay, so I'll quickly go over the data. It's much easier to do it here in the workshop. So this is a problem statement. Imagine you are an investigator at an organization that tracks financial crimes. You have 2 email addresses that have been flagged by law enforcement, and you need to do some investigation on those accounts that have those email addresses. So the main purpose of this is that you want to analyze the data and understand what is in it based on these 2 IDs that you have. And you're going to use pattern matching and recursive querying and a bunch of other things to actually understand what's in the data. And we'll visualize it, obviously, so that it's intuitive in terms of what the data has. So we have a finance network data set. We have persons, accounts. So person node is here in the middle. Person lives in an address. And person owns an account. And what this little curved edge here transfer basically means, an account transfers to another account, which makes sense. In the real world, you don't directly give money to someone. You put money into your account and then move money from your account to somebody else's account. So that's the schema or the schematic of what we're trying to do. And it's a very small data set just to make things easier to interpret. So we have 21 nodes of person, 21 accounts, 15 addresses, which means there are more than one person living in one address, and 21 relationships of the type transfer. And again, to make things simpler, they are in one direction only. We're not doing bidirectional relationships. So The data modeling aspect here is if you were doing an RDBMS, the first thing you would do in SQL or Postgres, whatever database you're using, is you would move your person CSV into a person table, account CSV into a account table, and then transfer is a connection between person and account, right? And we'll look at the data very briefly, actually. It's much easier to see that. So if I have this person CSV here, it has person and their metadata. You have an ID, name, address, state, zip code, and an email. And of course, email is what you're using to identify these so-called suspicious accounts. The accounts table is a lot simpler. You have ID, account ID, the owner, which is which person's ID owns this account, and the balance on that account. Also, the reason we have an ID column in the start of every file is you always want something that you can guarantee to be unique. So sometimes account ID can be that, no doubt. So to make life easier, I've just made all my ID columns as simple integers, but that might vary depending on what actual data you have. And then a transfer table which has source, target, so it's a relation table, and an amount of the transaction, and a random transaction ID, which is different from the account ID. So these are our three tables. So essentially what we're trying to do now is we're trying to transform this into a graph model. And as you know, you just have 3 CSV files, but to form a graph, and especially based on the structured property graph model in Kuzu that I described, if you look at this schema, this is what we're trying to do. So each of the nodes here would be represented by one table each. Person node table, address node table, account node table. And then each of the edges would also be their own table. Lives in, owns, and transfer. So you have 6 tables in total. And that's what I'm doing here in this DDL. If you look at the DDL, I'll walk through what we're doing here. DDL is essentially a data definition language. Every database, at least a structured database, has this approach. This is very similar to the Postgres dialect, where you have create table, except that in Kuzu you say create node table, because we're trying to differentiate node and edge. And the fields that we have in here are identical to what we have in the CSV, and we are assigning types to each of them. So IDs are ints, name and states are strings. In this case, it's US zip code, so we can get away with integers for this. And emails are also strings. Similarly, for address, we just have 2 fields, address and actually just the address. Because in this case, we're assuming addresses are unique, so we're just using that as a primary key. For account, we have account and a balance, and then relationship tables. So we call them create rel tables, owns, lives in, and transfer. And all we're saying here is from and to. So owns is from person to account, lives in is from person to address, transfer is from account to account, and I'm also giving it a amount value. So each transfer has an amount. So what I'm going to do is this copy statement is going to read data from the CSV, handle the escape characters and all the other things that you need. It's going to return what you need, and that is going to be ingested into each of the tables in Kuzu. So the first step was creating the tables. The second step is loading or inserting data into those tables. So that's pretty much all these lines are doing here. So it sounds like it's verbose or looks like it's verbose, but actually in theory, once you know what's happening, it's not that hard to understand. So once you have that, you can go into Kuzu Explorer, and I'm just going to copy paste the entire thing into this window, and I'm going to run it. So Shift Enter or press the green play button, either of those. That will go ahead and run this command. So I'll wait here if there's any questions or anybody has any blocks. Oh, yeah, sorry. It's in, if you've cloned the repo, it's in the DDL directory. And insert data kuzu.cypher. If anybody has any issues, please raise your hand. Sorry. Okay, so I want to quickly show one thing. I'm not sure if others are facing the same issue. So the moment I ran this DDL successfully, I got this display here, table has been created and all this stuff, right? So it's good. I can go ahead and throw away this cell. But just to show what happened, I have a new directory in my location now. It's called exdb Kuzu, so example database. And the reason it's called that is because that's what I specified in my Docker Compose. Right? My Docker Compose said that's the local directory that we are mapping. And even in my Cypher statement here, actually in this case, all I'm doing is connecting to it. So yeah, either way, the folder that I created is called exdb Kuzu. And inside this is all my data. All the data that I'm actually loading is actually stored in binary form in this location. So if I try to rerun this cell, let's say I copy paste this thing again and I try to rerun it, it's going to fail because I'm trying to insert data which has the same primary key. It's the same issue you face in a relational database. And it's a primary key constraint violation, so you cannot re-ingest the same data that has the same primary key. Now, you might ask a question, why does it not just overwrite? Why do I need to worry about constraint violations? And part of the reason for that is this is a data integrity thing. You want to be sure that you impose constraints on each node so that your relationship's integrity is preserved. In a graph, a relationship depends on the two nodes, it's the source and the target that it connects. So it's even more important that you maintain the uniqueness of each of those node IDs in a way that you don't have overlapping or duplicate data that you keep inserting in it again and again. So there are ways you can actually get around this where you can update the data and not actually overwrite the data. I think, Mel, you had this question. So for this workshop, we're not going to go into all of that. It's a data engineering issue. For this workshop, if you face this issue, the way I would fix it is I close my browser, I Control-C to get out of my Docker setup, and I delete the entire directory. This exdb Kuzu can be cleared out. I restart Docker Compose up. I type the same command again, Docker Compose up, reopen localhost 8000, and copy paste the same query in there again. So if you run that, you're going to have no issues. Did anyone face this, or does anyone not get this far? Okay, so I'll just show this next step just so that people can see what we are doing again. I mean, I don't want to just ingest the data and say we're done. So back to the README. So once the DDL is finished, I'm going to go ahead and do a basic visualization. I'm copy pasting this query here. This is the most simple query you can run in Cypher. All it's doing is saying match any node with any type of relationship attached to any other node in one direction and return everything. So I'm not specifying filters, no predicates, return the whole graph. But because that's a dangerous thing to do, if you have a billion nodes and you try to return everything, it's going to crash your system. So it's always a good idea when you do this sort of generic Cypher queries where you don't specify filters, use a limit clause to limit the number of nodes that you return. So I'm going to go ahead and return this. So before we go into this, I will, like you can see, it's not very, you just have numbers that are displayed on these nodes. So what I normally do is I go into the settings tab, I make the setting like the size a bit bigger, and I choose more interesting fields to display on each node. So in this case, I'm showing account IDs, addresses, and names of people. If I go ahead and save this, I can now go maximize my window. And because I'm on a shared screen, it looks a little weird. On your screen, it may look a little better. But essentially now, this is my overall graph. And here you can see that the green nodes represent, actually you can see that in the schema tab. Green nodes are accounts, blue nodes are person, orange nodes are address. And that's basically what we're showing here. Mary owns this account. She lives in this address. Looks like another person lives in the same address, and that person owns another account. So the graph can actually grow in a very interesting way, and you have a lot of interesting structures here. At a very high level in the center, like towards this portion, you can see there's a lot of crisscrossing connections among accounts. So we'll analyze that in a little bit more depth. I guess, please raise your hand if you have any questions. Okay, go ahead. No worries. Okay, so I think we'll get a move on. The interesting stuff has not arrived yet. So, okay, so I've gone through the graph visualization part. Now, I'm not going to expect anybody to run any SQL here. The goal of this workshop is not to run SQL, but I just want to do it myself because I will showcase the differences. But what we are going to do is we are going to write Cypher queries, and we'll spend about the next 15, 20 minutes doing some Cypher queries. So the first question I'm trying to answer is find all possible direct transfers to the account whose email is this. So you have some email address, and the question is asking, find direct transfers to the account owned by this person. So it's very intuitive. I hope the question makes sense. So I'll walk through how I construct the query for the first one, and then I'll slow down for the second one, and we can walk through the second one once people get going. So I'll open Kuzu Explorer again. So just remind myself that the question says direct transfers to the account owned by this person. So I'm going to copy this email address. A direct transfer is, if you look at my schema, person owns an account transfers to account, right? Now, this owns can be from either direction, right? An account can transfer to an account, so each person owns in only one direction, and an account can transfer to another account. So that is the direct relationship I'm trying to capture. So what I'm going to write here is a simple match statement. So match, start with person, so P1 person. By the way, the reason I do P1 with colon, so colon person is the syntax for type node. So type person, node table of type person. The colon tells it that's a node table name. And P1 is a variable that we are binding to, so I can access that its contents downstream. So match P1, similarly relationships, I'm going to say owns, and I'm going to bind this to a variable O1 onto account, so A1. So that's the first part of the query. I know person 1 owns account 1. Now I need to say there's a direct transfer to account 2. So I'm just going to do this. Account 2 transfers to another A2, account 2. But this time the ownership is in the reverse direction. So I do left arrow, O2 owns A2 account 2, right? But because I know what email address I'm looking for, and the question asks direct transfers to an account, the account I'm interested in here is A2, and the transfer was to that account. So I'm going to say where A2.email, sorry, not A2, P2.email. I messed up the second portion. I'm going to return star. So essentially that's what I've done here. I've returned the direct transfers to this account. In this data set, only one person has made such a direct transfer, which is this person called Carol. George is the person with this email. So George owns this account, Carol owns another account, and that account made a transfer to George. Direct here means path length 1. So this query is an explicit way of defining the path. You are directly saying, I know what path I'm following. I have person owns account, another person owns another account. This account has to be directly connected to the other account. So this T:transfer is the part where we say it's a path length 1 because it's a relationship. There is no clean star here. We're not doing any stars, recursion, none of that. Just a single direct relationship, and the direction is specified using this arrow. So transfer is from 1 to 2, and 2 is the person who we are looking for. So you can move around and you can inspect the data in a more clear way. And this gives an idea that, okay, so in this case, we have just one incoming transaction that is direct to this account. On its own, this is not a very useful question. So there are other questions we can ask. So does this query make sense? Are people able to run this query? Yeah. Sorry about that, yeah. So yeah, just to summarize, this is a explicit specification of the types of nodes and the length of the relationship that we are trying to do. So if you're not sure about what a particular clause does or how to use it, I recommend just going to this website, docs.kuzudb.com. That's our documentation page. And there's a search bar where you can actually say, okay, type in match. You get a bunch of things about match. In this case, let's say you forgot how to use the where clause. You could just say where, and so on. There's options for filtering and things like that. But in the repo, I kind of give some links to the relevant page in the documentation. So if the first query is clear, I'll go on to the second one. This is a little more interesting. So in this case, we're saying find all possible connections of the type transfer. So we are only interested in the transfer relationships, which is between accounts, including indirect transfers. So I don't need to transfer from just one account to another. It could be multi-hop between multiple accounts. And here I'm saying up to length 5 towards the same email. But this time we have another suspicious email. We have 2 emails that we are interested in, and go up to a length of 5 is what we are saying. So instead of constructing this query manually, which is, I'd rather not type out the whole thing, I have my queries here. So I'll wait for about 10 seconds, and if there's any questions, I'll go ahead, but otherwise I will construct this query. What we are doing here is we have a variable length query. They are called recursive queries. And if you look at the documentation, we have a page here that shows an example of such a recursive query, which I've already showed before, actually. The query here is, in this case, user follows user. The star 1.2 is called a recursive syntax. Star basically means go do more than one join. And .2 is go up to only path length 2, stop at 2. So that's basically what we're trying to do here. So this is a query that I have. I'm doing the similar thing like I did before. Person 1 owns account 1. This time I'm saying transfer star ... 5. So up to length 5, all the way to person 2. And this time you will notice that I did not specify direction. There is no arrow between account 1 and account 2. So these are called what's the word for that? Undirectional, non-directional joins, whatever. Like essentially, you're not looking at undirected relationships. That's the word I need. So the reason I did not do direction is if you look at my schema, person owns account is in this direction, account transfers to account is in this direction. But as the graph gets more complex, the transfers could be crisscrossing in different directions. So you don't want to have a situation where you hit an account and then that account owned by a person is in the wrong direction. So, sorry, where was my query again? Between 2 accounts, I'm saying I'm doing an undirected relationship. So regardless of whether it was from A2 to A1 or from A1 to A2, I don't care, give me both, right? Because I can't know upfront. When I'm doing this query, I don't know upfront whether A1 was transferring to A2 or A2 was transferring to A1. But I'm also specifying a predicate, which is P1 has this email, P2 has this email. So these are our 2 suspicious emails. And I'm returning this. I'm also calculating the size of this path, the length of this path, using the size function, calling it depth. And I'm ordering the result by depth. So minimum depth first. And now we can actually see that we are retrieving the interesting portions of the graph. Let's say George and Edward are the 2 persons who are under investigation. We have many indirect transfers between the accounts owned by them. We have this account here by George, this account here by Edward, and many other accounts. And what's interesting about Kuzu Explorer, what's useful about it is you could have run this in a Python script. Yeah, I'll come to your question in a minute. You could have run this in a Python script and gotten an output in a JSON blob or something, but this is visual. I can actually double click on a node that expands on this. I found this other person, she, who is also owning that account. And I can do a highlight mode where I can actually see which paths are on a particular node that I'm interested in. Right, so this is a very, it's a more exploratory way of thinking about your graph. So yeah, I'll go ahead and answer your question.
In this schema, the transfers, are they double accounted for, where a transfer between account A and account B would have 2 transfers, one going from one leg in and out, or just
Yes, so you're going to have a potential redundant relationship. So you might have account in A1 to A2, because you specified it as undirected, you're going to get all those nodes. You're going to get P1, O1, A1, T, A2, O2, P2. All of those in a sequence in one direction and the same thing in the sequence in the other direction. Yeah. And the reason that's useful is still useful is because if you did not do that, if you ran this with a direction, you would have identified a much smaller subset and you may not actually expand the paths enough for you to understand more, and you might actually just miss out on information. Yeah. So that's basically the meaning of a recursive join. And just, yeah, go ahead. Which value, sorry? So what I want to do is I can actually run this exact same query in a SQL database. So I'm going to make my life, I mean, your life a lot simpler by not asking you to do this. So I'll just demo this. So I can essentially go here and say open DuckDB, and I'm just going to open a SQL database. I'm going to run the DDL for the SQL. So the SQL DDL is very, very simple. It's so much simpler than the Cypher DDL, but that's mainly because our data model is very simple. We just have 3 tables, and we can just do joins on what we need from those tables. So similar what we had before, create table, select so-and-so, create, and keep adding. So that's pretty much what we're doing here. And I will go to my terminal. I will type this in here. So I've got my data in there, and I've already stored my queries here for query 1. In this case, I'm trying to answer the same query that I ran before that in Cypher, but I'm going to run it in a SQL database. You notice my answer is Carol, just like I had in the Cypher, the Kuzu query before. Similarly, the recursive query is what I want to go over. To actually get the result that I just got here in 4 lines of Cypher, and obviously this was intuitive where you understood what paths you were traversing, this is the actual DuckDB or the SQL query that you need to achieve the same thing. You start with a with recursive statement to begin the recursive join. We're calling it transfer paths. And the as syntax here is a CTE, context table expression. And it's kind of like a virtual table. You're creating a virtual table during your computation and then looping through that. So you start with the person that you care about, the email that one of the emails, but then you do a bunch of joins on these 3 tables to get the fields that you need. You do a bunch of filter matching on, attributes of each table, column names. Then you do a union all statement, and then define the actual recursion, which is traversing up to n relationships. I could have chosen n as any number. In this case, I've chosen 5. So I'm traversing 5 levels deep using a join. And then finally, I come out of that context table, CTE, and then I do a select statement on that table to the second email, which is of interest. And I return the results ordering by depth. So when I go ahead and copy that, I actually get a table result, and it's got 11 rows. And even though we could not see the number of rows in our Cypher query, if you actually go into the JSON output here, which is on the left, you'll actually count that, and it actually has 11 rows. So I verified that we return the exact same length. We have 11 paths, but the way you query that and way you retrieve that is obviously very different. And I don't know about you guys, but my SQL is decent. It's not great. So I spent about 15, 20 minutes on multiple GPT models trying to help it walk me through this, and it still made a ton of mistakes. So in the end, it was a painstaking exercise to construct this query with all these fields that I need and verify that I got nothing wrong. So that's just an example of what general data modeling is. Now, anyone who's worked with SQL and complex data modeling will immediately point out that you didn't have to model your data in this simplistic way. You could have normalized your tables, done an additional operation to move columns around in a way that you have a similar structure to the Cypher or the graph. And then your joins become much simpler. Very true, that's absolutely correct. But that basically means you have to do another ETL, right? You still have to take your data out of one table and move it to another table. What I'm saying is you could have just done that ETL and taken it to a graph and run a very intuitive, clean, easy to read Cypher query, reasoned about that query, and of course visualize your results. Because in the end, with a SQL query, you're never going to be able to visualize. You're only going to get a table, you're only going to get columns, and it's up to your mind to process what connections exist. So that's kind of what I'm taking away from this. I'll go to the third question. So I know we are, how much time do we have left? 30 minutes? Oh my God, okay. I'm behind schedule. So I won't, maybe what I'll do is, obviously the notebooks are fully available. Everyone can go through these. I want to go through the notebooks because they are particularly interesting and a lot of questions regarding machine learning. So I will go through that. But I will quickly wrap up this Cypher portion by going through another interesting query. So query 4 is very similar, 3 and 4 actually. It's using the shortest connection between these two addresses. So basically I'll just quickly run it. You guys don't need to go through each line. So it's these two email addresses. And the query I have is, I'm just using the same query as before, except that I'm just using the shortest keyword. That returns only the shortest paths, and I'm ordering it by depth. So in this case, I return just the one, and this is guaranteed that to be the shortest path between these two people. So as you can see, Edward and George are connected by 3 hops between their accounts. So even though I didn't specify the length of the path, the algorithm under the hood is computing the shortest path. Another interesting thing I could do is, instead of just saying shortest, I could use the all shortest keyword. And if I run this, in this case, all shortest also returns the same result. That's because there are no lengths or paths that are longer or shorter than this between these accounts. But what the next question is asking is, question 4 is find all shortest connections of any type between persons. So we are searching for any possible paths, not just transfer paths. And they can include other types of relationships as well. So the all shortest paths gives you this flexibility. But to run this, all we need to do is just change the intermediate path of what we're doing. So I'm just going from person to person. And of course, there's an error. Let me see what that is. Oh yeah, I forgot to specify the emails. So right, that's true. The transfer has to be removed. That's the main reason it didn't work. The reason the previous query failed, you're right, is because there is no path with that it does not involve, that involves just transfer between those people. Because now you have this interesting other path which is lives in. It so turns out that this person, Ria, lives in this address, George lives in the same address as Ria. So the point being, you're discovering other things about your data than just the transfer or account related information. You're connecting it to other entities from the real world. And I guess finally, what do we have here? Okay, so I want to go through 6 because 6 goes directly to the next one, which is the machine learning aspect. So this question is asking, find an important account that has the highest number of incoming transactions. So highest number of incoming transactions essentially is like, it's called degree. Like you have an in degree and an out degree. A degree in a graph is an incoming relationship or incoming edge, has an arrow pointing towards it. So that's called an in degree. And you're trying to find the node with the max in degree. So I will just take that query. I will explain that query in the editor. Just try to make this a bit bigger. Yeah. So the query is quite simple. It's essentially an account transfers to another account. In this case, I don't care about persons because I just need to find the degree of the account itself. And I'm counting the number of relationships, count T, naming that as in degree. Also note that the direction is specified here, so I'm counting it only in one direction. I order by the degree. I limit it to the top 3. Then I subsequently perform a match on only those limited 3 results to find the owners. So when I run this, I'm basically returning the names of people who have the highest in degree in the graph. Edward is one of them. There are 2 other people who have a high in degree as well. So on its own, this is not a very useful metric. You can't actually learn too much by saying, okay, 3 people have the same in degree. What does that really mean? So what the next query does is it extends on this. And instead of doing a degree count, I will explain that from the chart. So this question asks, find an important account that has received the most amount of money. The incoming transaction, the amount of transaction itself, not the number of transactions. So it's a very minor modification. Instead of doing a count, we are doing a sum. And we're doing a sum not on the relationship itself, but the property on that relationship, which is the amount, right? So it's pretty much the same query, except that I'm counting the amount instead of the number of relationships. And in this case, Edward is ranking higher than the other 2. He's got 8,400. The others have much, much less. So as you can see, they might have, the idea here is that one query gives you one aspect of the information, another one gives you another aspect. So using these different approaches actually gives you a holistic picture of what's happening. Now, using just Cypher to answer questions is interesting, but there are certain cases where you want to actually go deeper. You want to do some kind of graph algorithm, you want to do machine learning, you want to actually potentially train a model that can predict links between these nodes. There's many reasons you might want to do something more advanced than just querying on top of a graph. So that's kind of what the next question is doing. It's saying, find the accounts that are the most central, and it's using the concept of centrality in a graph. There are many centrality algorithms. The most famous one is PageRank, but I think PageRank is not very useful here because it's telling you the same thing that the degree told you, more or less the same thing. So what we are doing is we're going to use this other metric called betweenness centrality. And what betweenness centrality is it's the measure of the number of shortest paths that pass through a node. So typically centrality, just like a simple metric like degree centrality or PageRank, considers the number of incoming connections to a node. But betweenness centrality is not just looking at that. It's looking at how many shortest paths are passing through that node. So that's why the node becomes central. It's because when you count the number of shortest paths that pass through the node and then divide it by the total number of shortest paths in the entire graph between all pairs, that actually is telling you something about that node. So to run that, because there doesn't exist an inbuilt algorithm. So what we'll do is we will open an editor. I have my Python notebook here. I have a demo 1. So what this notebook goes through, and this is available for your exploration after this, is I will first clean this up and I will install my environment. I'll just verify that I have everything installed. I'm going to install Kuzu first, and then I'm going to do all the other requirements, which includes, NetworkX and all the other analysis libraries, NumPy and all of that. So I'm just going to walk through. I'm going to connect to the same database. I forgot to install kernel, so I'm just going to. Yeah, this is part of why I did not want to run a Python demo in this workshop, because it's never going to finish in a reasonable time. Okay, so I go ahead and run this. The first time you run, it's going to take a bit of time to compile because pandas and all that. But what we're trying to do is we're trying to isolate a portion of the graph. And like the part that I'm isolating here is I'm running the same query in Cypher, but I'm using the Python client now. So connection.execute this query. It's returning a subgraph of all the accounts that transfer to other accounts. And I'm returning that as a networkX object. So Kuzu directly outputs to the networkX format. And I'm going to run a betweenness centrality algorithm on it. So this BC is the values, like the tuples that it computes. Then I actually do a bit of transformation on it to see what I have. I use pandas to manipulate the data. I get this data frame that shows the node ID of account and the betweenness centrality value. So then I will run this simple alter table command in Kuzu to add a betweenness centrality property to my account table of type float, and its default value is 0. The reason I need to do this is because Kuzu is a structured property graph. The only way you can actually add a new field that did not exist before is tell it that now there's a new column. So that's what this alter table does. So if you're coming from a system like Neo4j where this schema is not important, this is typically not done. You can add a new property on a node that did not exist in other nodes. Kuzu is a lot stricter about that. And the reason it's, as I mentioned, is strict is because of the performance aspect, where a column needs to be known beforehand. You need to know what column exists. You need to know what data types are in that column. That's why I specified the type double, which is a float value. And I also use the alter table command to modify that table. So I'll go ahead and run that. The table has been altered. And now this is a very interesting feature where I use this load from command, which is a open Cypher syntax for scan from an existing file or entity. In this case, I'm scanning from the data frame. So I'm taking all the values from that data frame, casting it to the types that I need, using the merge command in Kuzu, which is like an upsert operation. So it's looking for accounts with that ID. Merge is saying if the node is matched, set the value of betweenness centrality to the value that I just have. And then I return the full result to verify that it actually worked. So this is basically running the data, ingesting it into the graph, outputting the result so that I know that the data is actually in the graph. And I'll verify that in my Explorer window as well. So once I have this, I see that there's one particular node here, account ID, that has a much higher betweenness centrality value, 0.45, compared to any of the other ones. And if I were to go back, I think I might run into an issue here where let's just see if I can run this query. Okay, it works. Okay, so all I'm saying is I'm going to match account A1 transfer account 2, where account 2 dot account ID is that value. And I'm also going to say I want to find the owner of that account. O1 P1 dot name. Or I should say distinct because there's many such paths where that match was obtained. So essentially, this account is owned by the person Amanda. So I'm just going to say return distinct star actually. So that's easier. So there's 3 such paths that lead to Amanda. So what I'm trying to understand from this is this person has a much, much higher degree centrality value. And that becomes apparent when you actually look at the entire graph. The one that we had before, which is match A C. So if I were to zoom in to the portion, I know it's hard on the screen, unfortunately, but if you had a much larger monitor, it's a lot easier. Where is that? Yeah, so this is the person we are after in this case, and her account is this one here. So I'm going to drag that out further out. As you can see, there's a lot of incoming edges, and also it's in a portion of the network where there's a lot of other indirect transfers going through that account. So that's why it has such a high betweenness centrality. The nodes on this side, the account nodes on the right side of this graph, have a much, much lower value because there's not that many paths going through them. So you could have looked at this qualitatively, but now through the algorithm, you're able to actually get a quantitative number that you can assign to it. And now that value is actually stored in the graph. When you double click on this node, there is now, well, okay, I need to refresh the graph, but basically the value has been ingested back into the graph. So that's regarding the betweenness centrality. I'll open the second notebook that showcases the machine learning aspect of it. Now, I'm not obviously going to train a model, but what I'm trying to show here is I have an existing graph. I have a database directory in which all that data is sitting. So my graph is in that directory. It could grow arbitrarily large. This directory could be on a cloud machine. It might be having millions, if not billions of nodes, tens of millions, if not tens of billions of edges. And all you're doing is pointing to that directory saying, this is where my data sits, and getting a connection to that database. That's the first step here. What the next step does is there is a new method, or like a different way of thinking about working with PyTorch, which is now that you have your data already in a graph, you already know the connectivity of that data. So what I'm doing now is I'm just going to close my Docker container. I don't need that anymore. I'm just going to run this with the same kernel. Yeah, this is the read-write issue that I was talking about. The reason it doesn't let me open this is because Kuzu is an embedded database. So when one process is writing to the database, it does not let another process write to the same database. There's this lock file that gets created. Right now, my Explorer window had it had acquired that lock. All I do is I delete this lock, and now I'm able to go ahead and rerun this. So that's really important to understand, because in a graph, you cannot have two processes writing data simultaneously, two independent processes writing data to it, because you might have inconsistencies between nodes and edges. If you're trying to write an edge from one process that on a node that does not exist, that has not yet been written from the other process, it's going to cause all kinds of issues. So that's why this lock file exists and why we prevent multi-process writes. On the other hand, reads are not locked at all. You can have arbitrary number of read processes concurrently reading from an existing database. So what's typically done in a production situation is you would open a read-only connection using this, I think there's a connection or something. Yeah. There is a keyword argument on a database, so you can say connection is read-only, and then you open a connection, any number of connections to that database. So that's just what I did here. The next step is I'm using the database as a PyTorch Geometric remote backend. So when I run this command, I'm converting it to a feature store and a graph store. These are the two objects that I extract from the graph. And the reason it's taking this long is not because the graph is large or Kuzu is slow, it's because PyTorch takes forever to compile. It's a Python thing. So go ahead.
So you told that you can have as much as we want for read request, right?
Yes.
So if during that read request, some other processes are just writing and editing the, for example, data.
Yep. So the question is, if we have arbitrary number of reads and some other process modifies the data, what happens to the integrity of the read, right? It's perfectly fine, because in the end, Kuzu is ACID compliant. It's like any other relational system. So what that means is there is a write-ahead log. The data that is being written is stored in the write-ahead log. It's guaranteed to be committed once a transaction succeeds. When a read process is acquiring that data, it's not restricted by that. So at the moment the data is written, it is immediately available for the read process. So you might have one write, but 20 read processes happening concurrently. All those 20 are non-blocking. The write is blocking, right? So the read will immediately take the value that is available once the write-ahead log finishes its operation. It's like any other ACID transaction.
So if during the writing we just request two reads, for example, we can see, the results are not the same, right?
Yeah, so when you say during the write is once a transaction commits, it's a before and after situation. Yeah. So before the write finishes, you will retrieve the old data. The moment the write finishes, you will retrieve the new data. It's like a transaction. It is basically ACID transactions. Yes. So the feature in the graph store is really interesting, because what we are doing is we are storing a feature store that has all the property information on the nodes in the graph. And in this case, I'm displaying persons, accounts, features. You'll notice here that only a subset of the properties we had in our graph are displayed. That's because these are all tensors. At the end, everything is compiled down to a tensor in PyTorch, and you have float values or integer values that can be converted to tensors. Strings obviously can't. So what the feature store is doing is any numerical value or property that is on a node is converted to a feature, and you're actually storing those as an array of tensors, like a tensor that has all these individual values inside it. And you can access individual tensors that way. I can say, give me the account values balance tensor, and this is giving me the entire graph's representation of that. These are essentially the features. And then I also have a graph store, which has the edge indices. So an edge index contains information about the triples, which is person lives in address, account transfer account, person owns account. And this is where we are actually looking for users to actually give us some feedback, which is PyTorch Geometric has multiple definitions or multiple kinds of edge layouts. The one we've implemented currently is COO. There is also a CSR, compact sparse representation, compact sparse, forget the full form of CSR, but that is a more commonly used edge index in a graph. And internally, Kuzu uses a CSR representation for its edge index. So in theory, it's very straightforward to transform the CSR edge index from Kuzu into a PyTorch version of CSR. The reason it's not available in this current release is because when we first implemented this, PyTorch Geometric was going through a refactor in version 2. And at that time, the CSR was not fully available. So this is something that is very much in the pipeline. And users who want to do a CSR type edge layout for an edge can easily do that. Go ahead.
In terms of optimizations that are like the biggest schema, where is all the effort put into? And the things like tensors before, I saw that they were split 64s.
Yep.
The things like quantization of those vectors end up improving performance a lot, or these things the performance gains somewhere else in theory?
So my understanding of PyTorch, so we offload all of that computation portion of it to PyTorch, right? At the end, the library that does the machine learning is PyTorch Geometric. Kuzu does not do the machine learning. It is just acting as a feature and a graph store. So from what I know about PyTorch Geometric, they have a mixed float representation. They support a combination of FP16 and a couple of other formats. I forget the exact name of that mixed floating point representation. So currently, we only support float 64 transport of data between the storage layer to PyTorch. But in theory, it should be possible to support mixed floats.
Is that because you're storing the tensors?
Yes. Yes, by nature, tensors are stored in float 64 to avoid precision loss. But yes, that of course has computational cost and storage costs.
Yes.
Yep. So that's definitely something that it's not a technical challenge to potentially use that in the future. So all I'm doing here is I'm showing what an edge index looks like. All it's storing is the index values of this representation. So what I want to highlight here is we have a tutorial page in the documentation that I linked to in the notebook, where we actually go through a lot of what I've just covered. We cover intro to Cypher, network X, including reading and writing. So you take data out and bring it back in. When we release the graph algorithms package in due course, there will be another similar notebook that shows how to use graph algorithms from within Kuzu without taking the data out, because that's way more scalable than using network X. And then, of course, PyTorch Geometric has multiple kinds of use cases. We have node property prediction, link prediction, multiple kinds of models to be trained. The goal is to add a node embedding training model example to this as well. So I highly recommend going through some of these examples in the documentation. It's docs.kuzudb.com. And the only final thing I want to do in our last few minutes is talk about this, what we're doing in terms of GraphQA. There's a lot of stuff in the pipeline that obviously I can't go through here. But what I'm doing with this is, actually, to remove that lock situation, let me just close my notebooks. I'll only have one notebook open. I'm going to just showcase with the same data set what I'm doing in terms of GraphQA using an LLM. And so I have an OpenAI key that I've put into my environment file, so I can actually technically use this. But I need to make the imports, obviously. So what we're doing essentially is just like we passed the graph backend in Kuzu to PyTorch Geometric, we're doing it now with LangChain. So we are essentially defining a Kuzu graph class in LangChain and defining a schema, like storing the schema of the graph, what properties we have on our nodes, what relationships we have, and what properties are on those relationships. This is useful information that we use as context to the LLM. And now we can just use a Kuzu QA chain class where we specify an OpenAI model and ask a question in natural language. Like in this case, I'm asking a question, what is the highest amount transferred in the data set? And it will obviously construct this query based on the schema that I used in my prompt. So it's very important that this step, I mean, obviously this is the same process you use in any graph database, not just Kuzu, but the schema information is invaluable context where this query that gets generated actually has that context. And even despite giving it context to the best of our knowledge, there might be issues with directionality. Most of the time you have query, the direction of the relationship captured correctly in the LLM cipher, but essentially you have a max, in this case, we're just returning the maximum amount, which is $7,000. Now, where it gets tricky is you can ask it slightly more complicated questions like, there are two persons, Carissa and Anna, is there a path up to a length 3? And I can go ahead and run this. And does it say the answer? Oh yeah, apparently I got an answer for this one. So it ran this query, path query, where it figured out the recursive join up to length 3, 1.3, between these two names. And you might wonder, how did it know that the name property is what it should use? It could have used any other property, right? The reason is because the schema was in the prompt. The schema has to be a part of the prompt. So what I've experimented with is I've also gone into hosting like local LLMs, the GGUF models. Go ahead.
When you're doing those queries, are you doing anything like grammar constraint generation for the actual?
Good question. There is no grammar constraint generation. What we've seen users do in our case is they have a intermediate step in the pipeline for grammar checks. And actually, the OpenCypher grammar is open source. This is based on a grammar that is available publicly. So what people have done is they take the query generated by the LLM, pass it to the OpenCypher grammar checker. That's a rule-based system. And if the query is incorrect in syntax or incorrect in direction, the grammar will fail. You will have a syntax error. And the LLM is basically given that as context. The syntax error message is passed to the LLM, and you have a two-step process where the LLM generates the query again. And from what I'm hearing, that works pretty well.
Yeah.
Yep. Okay, we'll talk offline. Yeah. And what I want to end with is the idea is cipher generation is great. Like you have text to SQL, you have text to Cypher, you have all these ways of generating queries using LLMs. And speaking of which, I forgot to mention, we have this feature here in Kuzu Explorer where I could have done the same thing. I could have just asked this question, which addresses have the most people living in them, and pasted that here in the cipher, in the editor. And in this case, okay, I closed my editor, but it's not going to work, is it? Okay. Yeah. So what it did is just like we have an OpenAI manual code that we wrote, we have a backend that is running on Kuzu Explorer that has its own GPT generating, contacting script. And the way you access it is you go to the query generation options in settings. There's an API key here. And you're using either a GPT 3.5 Turbo or a GPT-4 model. From my experience, GPT-4 is expensive and overrated for cipher generation. So I generally don't I just use GPT 3.5 Turbo. And there are other models that you can piggyback off of Grok, which is a much faster way to generate these queries. So yeah, I highly recommend trying out those pipelines. But currently in this interface, only OpenAI models are supported. If you want to use other LLMs, you can always link up with your own custom Python code that does that. But this is actually a great way to also learn Cypher. You can use your API key. Each API call is like a fraction of a cent. Like I've been using this all month and I've hardly spent $1. So I think it's definitely underrated. You can use it to learn Cypher a lot more efficiently. Okay, so I know I'm out of time. I'm just going to wrap up in a very quick minute. All I want to end with is this particular takeaway, which is I think the reason graphs and graph databases have not reached the level of adoption that people wanted is usability. And of course, there's a cost angle to it, but usability is a huge part of it. People who work with machine learning know this every day. Like you know what models you want to train, but then how do you get the data in a form and shape that you need? So what we're trying to do here is usability is at the forefront of the design of Kuzu. There's a property graph model. There's also an RDF wrapper on top of the property graph model that I didn't go to. But if you do work with RDF models in graphs that are useful for knowledge graph representations, that is also a possibility within Kuzu. And that is also queryable within Cypher, which is, I think, the only product which allows both. It's embeddable, which is similar to DuckDB and SQLite. So that does not mean that it is meant for small graphs. It still scales to very large graphs. It's lightweight yet performant. As I mentioned, there's ACID transactions, so your data integrity is not in question. The license is very permissive. It's MIT licensed. And the interoperability is a huge focus. We not only integrate with DuckDB and Postgres, but there's a lot of other database integrations in the pipeline. There's a very interesting project ongoing right now internally where we are trying to build a query engine on top of Postgres. So essentially, you can run a graph query engine on your Postgres tables without actually doing the ETL to move your data into a graph. When that actually comes out, it's going to be really exciting because I think that's where the space is going. Interoperability is the name of the game these days. And of course, no graph product would be complete without integrations with all the important ML and AI frameworks. And currently, there's a lot of ongoing PRs with LangChain as well as Llama Index to help people generate graphs from their unstructured data. In fact, I'm myself working on some of those. So I haven't had time to cover what we're doing, but yeah, if you want to chat about more of those use cases, we can chat offline as well. So yeah, I really hope that people take something from this. And please go ahead and pip install Kuzu, start us on GitHub. I also want to mention one last thing, which is a YouTube series that we are going to be releasing. Actually, we've released part of that series. It's called Fundamentals of Graph Databases on YouTube. So our channel on YouTube is @KuzuDB. And in the next few weeks, we're going to be releasing hands-on practical implementation examples similar to what I've done here. In fact, I might turn this into a YouTube video myself. So yeah, please follow our channel and go ahead and check out some of that content. Yeah, thanks a lot.